In this video, we'll discuss the operating mechanism of vacuum pumps that are commonly used in semiconductor fabrication tools. Specifically, we'll do so by explaining the operating principles of three types of vacuum pumps. Those vacuum pumps are the scroll pumps, turbo pumps, and cryo pumps. Vacuum pumps are generally classified according to their operating principles into two categories. The first category is the gas transfer vacuum pumps. As the name indicates, the vacuum pumps in this category collect the residual gas molecules from the chamber and then transfer them to the ambient air through an exhaust. The second category is the entrapment vacuum pumps. In this category, the residual gas molecules are collected from the chamber and then entrapped inside the vacuum pump itself. A well-known example of this category is the cryopump. The first category has two major subcategories: positive displacement vacuum pumps. A prominent example of this subcategory is a scroll pump. The second subcategory is the kinetic vacuum pumps, with a prominent example of turbomolecular pump. In the remainder of this video, we'll delve into the operating mechanism of vacuum pumps by reviewing the operation of the scroll pumps, turbomolecular pumps, and cryopumps. Let us begin with the scroll pumps. The scroll vacuum pumps typically consist of two main spiral-shaped components, referred to as scrolls, where one scroll is fixed and the other one is rotating with respect to the fixed scroll. This short movie here illustrates the operating mechanism. The movement of the rotating scroll with respect to the fixed scroll causes the transfer of gas molecules denoted as blue particles from the process chamber into the outer region of the pump and then into the center of the pump. These gas molecules are finally discharged through the exhaust port at the center of the fixed scroll. We next review the operating principle of the turbomolecular vacuum pumps. These pumps are used for achieving high vacuum to ultra-high vacuum levels. The operating principle of these pumps is also based on gas transfer. At the molecular flow regime, a molecule striking a surface condenses, rests, and re-evaporates in a direction independent of the incident. The vacuum range at which this phenomenon occurs is below 1 millibar. With this background, let's review the operation of a turbopump with the help of this short movie. The top port of the turbopump is connected to a process chamber that is intended to be evacuated. The bottom port, on the other hand, is connected to an exhaust through a scroll pump. Now let's look inside of a turbopump. Looking inside of a turbopump, there are two types of discs that are stacked alternately on top of each other. One set of discs are rotating and spinning in place around the shaft. These discs are referred to as rotors. The other set of discs are stationary and are known as stators. As the residual gas molecules, the blue particles here, enter from the process chamber into the pump, they may collide with the stator and deflected toward the upper rotor disc, as shown here. Upon a collision with the upper rotor disc, the gas molecule changes its trajectory again and downward toward the exhaust. As you can see here, the blue particles, the gas molecules, go through alternately this process and get evacuated from the exhaust. Let us now review the evacuation procedure of a vacuum chamber using a turbopump. The illustration here shows the diagram of a pumping system. In this diagram, the scroll pump is connected to the vacuum chamber through a dedicated vacuum line. Furthermore, the scroll pump is separated from the vacuum chamber through a pneumatic valve. The vacuum chamber is also connected to a turbo pump, which is separated by a pneumatic gate valve. Furthermore, the turbo pump is connected to a scroll pump and isolated using a pneumatic valve. In this example, the chamber initially sits at the atmospheric pressure. Therefore, the first stage is to reduce the pressure of the chamber from the atmospheric pressure to below 1 millitorr. This is done by opening the valve between the scroll pump and the chamber. In this stage, it is crucial to ensure that the turbo pump is isolated from the chamber as well as the scroll pump by ensuring that the pneumatic valves are closed. Failure to follow this procedure may result in permanent damage to the turbo pump system. Once the pressure in the process chamber reaches below 1 millibar, it is safe to continue the evacuation using the turbo pump. To do so, the chamber must first be isolated from the scroll pump by closing this valve on top. Then the valve between the scroll pump and the turbo pump should be opened, and the acceleration of the turbo pump starts. Subsequently, the gate valve can be opened to resume the evacuation of the chamber using the turbo pump with the backing of the scroll pump. Now let us consider the cryopumps as a third example. Unlike the gas transfer pumps, the operation of cryopumps is based on gas entrapment. The movie here illustrates the operation. In principle, a cryopump consists of cold inner components that are responsible for trapping various residual gases such as water, nitrogen, and hydrogen. The temperature of these cold components should remain below 20 Kelvin. As the gas molecules are frozen, they are unable to return to the process chamber. However, the inner components have a limited surface area. Accordingly, these surface areas become fully covered by the frozen gas molecules over time. As a result, the cryopump begins to lose its efficacy in evacuating the process chambers. To remedy this issue, the cryopump is warmed up to room temperature through a process called regeneration. This slide here shows an example of evacuation using a cryopump. Pumping is performed in two stages. In the first stage, the chamber is evacuated to low vacuum using a scroll pump, while the cryopump is isolated from the main chamber through the gate valve. Once the medium level vacuum is reached, the scroll pump is isolated from the chamber, and the gate valve between the cryopump and the main chamber is opened. Notice the temperature of the cryopump in this example, which is about 14.7 Kelvin. Our discussion so far focused on the required pumping systems for achieving high vacuum and ultra-high vacuum levels. However, another important requirement is the quality of the overall vacuum system. Various sources of leak and outgassing can degrade the quality of the vacuum. The outgassing can happen due to the gradual evaporation of contaminations such as hydrocarbons inside the chamber. The presence of vacuum leaks also degrade the quality of the vacuum. It is therefore crucial to ensure the integrity of the vacuum chambers in high vacuum and ultra-high vacuum system through a process called leak testing. The leak testing of vacuum systems can be performed using mass spectrometers. There are two main approaches. The first approach involves using leak detectors. In this approach, helium gas will be sprayed at different parts of the vacuum system. The rise of the helium level will be detected by the leak detector unit and indicates an external leak in the system. This approach is, however, unable to provide information about possible issues such as outgassing. Alternatively, the leak test using a residual gas analyzer or RGA can address this shortcoming. In addition to the helium spray approach, by spraying helium at different components and parts of the vacuum system, the RGA unit can also be used to obtain information about the gas content inside the chamber. Specifically, this analysis can be useful for quantifying the amount of residual gas molecules in the chamber. This capability is very important, especially in circumstances that the residual gas molecules have adverse effect on the fabrication process, such as material synthesis. To conclude this discussion, it is important to reiterate that vacuum systems are pervasive in semiconductor manufacturing. They're commonly used in various machines, from reactive ion etchers to evaporators to e-beam lithography systems. Therefore, understanding the principles of vacuum systems is crucial for properly operating semiconductor tools.